No, it was really great to hear the last talk. I was at Carbon before we started C Infinity, and at Carbon I was working on design engine, which Andrew talked about, which is very cool to see how far they've gone. So at C Infinity, we're thinking, there's already so many challenges in making parts, as you saw from the last couple of conversations. And designing a part can involve a lot of analysis of physics and customization, but a lot of challenges still remain when you go from parts to assemblies. And so what we're looking at C Infinity is really thinking about how to overcome the complexity of manufacturing assemblies. And one of the things that people talk about a lot right now is physical AI. And physical AI is basically autonomous hardware operating in the real world. And so one of the biggest use cases of physical AI in manufacturing is in robotic assembly, and how robots can actually take complex products, customized products, and assemble them together. But the challenge is that the provenance of these assemblies comes from design. And designs are created in 3D CAD systems, as we all know, and you have digital 3D assembly, and the output of the design process for an assembled product is what is called an engineering bill of materials, or an EBOM, right? Like this is the standard terminology they use in Product Lifecycle Management. So how does the EBOM actually go into the set of instructions that actually are used on the factory floor to be able to make the assembly? And that's a really messy process today. And it's a problem that we solve called process planning. And fundamentally, it's a problem about how to convert one structure, one representation of a product into another representation. So the EBOM is the engineer's view of the product. It's a functional breakdown of the product into sub-assemblies that typically have their own distinct functions, like a hydraulic system or pneumatic system or structural system. But that needs to be converted into the manufacturing bill of materials, called the MBOM. And today that process is entirely manual, right? You use PLM systems and you use a lot of, very, very archaic techniques like creating exploded views and PowerPoints and screenshots, and it's really, really painful and it's messy. So solving this problem of converting the EBOM to the MBOM is quite fundamental in manufacturing, but it is also something that we abstracted about. And saw that it is a sort of a general problem that we must solve. When there is intent that needs to be converted to instructions, that's what a compiler does. And if you look at software programs, you represent your intent in terms of a programming language, and a compiler works by taking that representation of your intent, mapping it to your architecture on which you're actually going to execute your instructions, and creates that sequence. So what we're building at C Infinity is a product called AutoAssembler, which we're calling it as a compiler for physical artificial intelligence. Okay, so I'm going to talk about how we do that now. So after we started C Infinity, we spent a whole bunch of time with manufacturers at scale. So we worked with some of the Fortune 100 manufacturers and people who are really advanced and savvy in terms of how to bring modern techniques into manufacturing. Modern software techniques into manufacturing, but you still see that there is so much that needs to be done. Designs that come out of various design departments that need to go into manufacturing, they're filled with bugs, right? Like there are all kinds of unintended interferences, there's alignment issues, there's all kinds of issues going on. So if you think of the analogy to a program, right, like that program is basically filled with all kinds of errors, right? Like, and you need, one of the things a compiler can do for you is to be able to uncover those errors and to understand like where you have, let's say, syntax errors, for example, right, like in your design. And so debugging source CAD early and quickly is something that is very valuable to a design engineer. And it avoids a lot of painful iterations. The process today is you go through a design review cycle and you might uncover these issues sometimes, but you want to uncover them early. The other challenge is that in CAD systems, or in the design process, typically we start from parts and we go all the way up to assemblies. And so it's a bottom-up process. And the assembled products typically are what you get out as the final product. And so discovering issues in the design at the assembly stage can often force really expensive redesigns and triggers all kinds of emergency design reviews and so on.
So you want to be able to overcome that and identify issues early. The other problem we've seen is that products, are increasingly customized and configured, like we heard from the previous conversations. And so this is happening at the assembly level too, right? Like the simplest example is if you want to buy a computer, you can configure your GPU, you can configure your hard drive and whatever, right? Like, so you can do that not just for simple consumer products, but you can also do it for like really complex, like off-road automotive products and semiconductors and so on. So when you have multiple configurations of a product, every change you make to a design ripples across all of those configurations, and they can affect the manufacturability of a whole product family. Now you're thinking about not just a single design, you're thinking about a class of designs. So how do you manage that kind of complexity? So we said that like, if you can actually constructively define a process plan from a design, take a design as the input and generate a sequence of operations that can be used to make that design or assemble that design in our case, it is a constructive proof of design for assembly. And so if you can construct that proof, then you at least have a valid assembly sequence or a valid process plan, but if you can't, you have an issue. Now going from design to manufacturing, you want to be aware of how the products come together in your specific factory. Like if a company has production lines in, say, Indiana versus Brazil or Germany, right? Like those factories are going to look different. And the way material flows in each of those factories is also going to be different. So you want to be able to capture that information as a part of your compilation target, as I call it. So how does AutoAssembler work, right? Like, so it works inside your CAD program, and here I'm showing Creo, for example. And so what happens is you take your 3D model and you upload it into AutoAssembler inside your CAD program, and it comes up with an automated sequence of operations, right, like of installation operations. And so it'll basically come up with it figures out the relationships between the part geometries, understands how they can be moved relative to each other, understands the precedence relationship of what needs to come before what, and organizes all of that into a coherent process plan. So to show how that works out, right? Like, so if you create a new plan, and in AutoAssembler you can create multiple what-if scenarios. This is something that design and manufacturing engineers love to have, right? Like, so they can collaborate and have a conversation about how to converge to the right plan. So in a what-if scenario, in a new scenario, you can construct a plan for each sub-assembly. And you can customize your plan to be able to create specific groupings of parts. Now, groupings is a way in which we do design. Like, for example, you have bolt patterns and mirror patterns that you see all the time in design geometries, but you also use it in manufacturing to be able to convey the right kind of instructions. So similar parts need to be treated similarly, in a process plan. So we can create that level of specificity inside the process plan, and the planner is fast and it adapts immediately to be able to take in human input and recompute a process plan that actually works. And the next challenge in the EBOM MBOM conversion problem is you have to be able to adapt your structure to the manufacturing line. So in this case, what I'm saying is that let's just go back here. What we're trying to show here is that if you look at the structure of the assembly, I want to make sure the designer has said that the timing cover and the water pump, these two sub-assemblies over here, are distinct sub-assemblies, but the manufacturer says, you know what, I'm going to take all of these parts together as a bag of parts and make them together in a single assembly cell, right? So how does that work out in AutoAssembler? So you can move your design structure and reorganize it and try to construct a manufacturing plan, right? Like, so you do that and you construct a plan for the water pump and the timing cover, you get a new plan. Now here's an example of a bug, right? Like that happens. So what you see is that like you have a bunch of parts that belong to a bearing that are shown, in red. So why is that? So AutoAssembler says that, well, you know what? Like the design of this bearing has the balls of the bearing inside the bearing race, and there's no way in which I can assemble this. So, but what happens in this case is that this is actually a part that I got from a supplier, right? And the suppliers, they don't give you your entire CAD models. So you can say, this is a pre-assembled geometry, don't try to construct a plan for this. An auto-assembler is going to, work with those constraints and create a plan for the rest of it. And the third thing we see from engineers, or requests from engineers, that they want to customize plans. So they say, yeah, this is great, but like I want to take, the shaft over here, and I want to move it all the way up right after the impeller, because I want to use the shaft to align the parts that come after that in the assembly sequence. So you can reorder the plan if you like. So it's like a human AI partnership over here, where the human engineer says, like, okay, these steps in the plan need to be updated, and the artificial intelligence solver can figure out whether that plan is valid or not, and comes up with the right sequence. And the next thing that AutoAssembler does is it's introspective, right? Like, so it looks at what it can do with the plan, and it says, there are some places where I just simply can't construct a plan, and I see some interferences here, but maybe you know how to solve it, human. Right, like, because it might involve some complex motion of some really flexible geometry that I can't really figure out in a meaningful way. So the human can override the AI's roadblock effectively, and then the AI progresses with the plan to come up with the updated sequence. So there's all kinds of things that we do inside AutoAssembler to build this collaborative intelligence between the human engineer and the automatic planner, that become very useful to the process of converting the EBOM to the MBOM. So we call this building AI with mechanical intuition. The output of AutoAssembler is a set of instructions that are directed either towards humans or to robots. Human output is presented in the form of work instructions, and robotic output is presented in the form of joint angles and programs that you can use to actually construct the sequence. So this is it's mechanical intuition because we take the design and infer the design intent from it. We figure out how the parts were supposed to move together or interact with each other from just a geometry specification. Converting the language of geometry to the language of motion is a challenging problem to solve, and we were able to overcome some of those challenges. And you see that it is a collaborative tool, so you can work together with the AI to construct your process plans and output the instructions. And this, it's been a year and a half since we started the company, and the solution is already deployed in some leading manufacturing companies, including a couple of Fortune 100 companies, right? Like, so they're using it as a part of their day-to-day process. So the challenge in this EBOM to MBOM conversion can be seen in this diagram, right? Like, so this is the engineering design representation of the assembly tree, and this is the manufacturing representation, right? Like, of how the parts need to come together in a sequence. And the transformation is what we can do with AutoAssembler. And now we get to the next level, right? Like, configurations, product configurations, and how do we manage them. So as I said before, there's a lot of customization for hardware products. And in the picture above, I have 3 examples of a fairly simple assembly that has 3 distinct configurations. Variants of products are created all the time for customization, but from a manufacturing point of view, you want to reuse existing knowledge as much as you can. Right, like, so if you have a product where some of the subcomponents or subassemblies are reused, you don't want to redesign or recompute a manufacturing plan or an MBOM for those subcomponents, and you want to be able to take advantage of what you've done before. And this is especially true in high-mix manufacturing, right? So this is where we get into the concept of a configuration space, right? So in a lot of in the early days of robot motion planning, what people tried to do was to define what is called a configuration space, which is basically all the possible states in which a robot can move in, and try to partition it into regions where the robot cannot move versus where the robot can move, and then figure out a motion plan, in that space. So it's the same concept that can be applied to product assemblies. Right? So if you have variants of products, you want to think about like how they can be organized in such a way that some design modifications are infeasible, and whenever the modifications are feasible, you want to reuse existing knowledge. And what we do to solve that problem is to use machine learning to create a representation of your entire product variant space. So one of the things you can do very well with machine learning is create embeddings of geometry. And when you have embeddings of geometry represented as a data set, then you can, as a database, then you can query and pull from existing geometries to do surgery, as I call it. So you have like, you pick and place the components of a plan that you need to and stitch it together to create your new MBOM representation. So this allows users to generate output 10x faster than they can today, right? So this is a really effective procedure. I'll go really quickly through this video to show you what the reuse looks like. So here is one variant of a design, and we've constructed a plan for it. And once you've constructed this plan and you save it, the next variant is going to look at it's something that's very similar to what you've seen before, except the piston is in a different configuration, and it reuses the plan for the piston and the back plate in this case, and it only plans for the things that you actually have not seen before. So reuse and reconfiguration are two big parts of how you can speed up manufacturing planning. And ultimately how AutoAssembler works is that like it takes in a design, takes in a library of existing plans, which reflects the topology or the layout of your shop floor, takes that together, constructs a process plan after giving you design for assembly feedback, and the compiler's output, which is an MBOM, is then fed back into the library to learn continuously about your enterprise's know-how, essentially, and then you compile it further down into factory-specific instructions. So the reason why this is powerful is because you can deploy it, and we deploy it in virtual private clouds. We don't cross-train on manufacturers' data. So once you run it a few times and you see MBOM output, the quality of the plans just starts improving rapidly after that. And I want to connect this back upstream. Why we started solving this problem, not only is it a pain point today, and where this is going is upstream towards design, right? And yes, planning is a constructive proof of design for manufacturability. Yes, it's a pain point. But where I see the real advantage of this approach is in simplifying complex systems. And one of the ways to simplify complex systems is through parts consolidation. And when you try to figure out how to reduce cost or reduce the number of parts, it may not always be the same thing. But if you're trying to reduce the number of parts and create these nonlinear system improvements, how do you identify the collection of parts that needs to be consolidated? Planning gives you insight into that. If a collection of parts can be put together in the same assembly sequence, right, and if they have similar material properties, then that's a good candidate for you to think about in terms of parts consolidation. And thinking about it one step further, maybe you uncover new manufacturing processes, like how Tesla did with the GigaPress, right? Like they took the undercarriage of the Model Y, and from 300 parts, they made it, I guess, 2 parts, and now 1 part using a stamping machine, right? Like a large-scale stamping machine. So this coupling between design and manufacturing can only be identified if you look at the assembly level, if you look top-down into the manufacturing process. And so that's kind of where we're seeing this go. So we want to unlock system-level efficiency, search a product configuration space, compile intelligently to get process plans to transform the EBOM to the MBOM. It's a huge problem, $50 million year over year for large manufacturers, and get to the point where we can compile it all the way to physical AI and go upstream to design. That's our vision for C-Infinity. If you're interested in talking more about AutoAssembler and C-Infinity, please talk to me after this.